Today we're going to talk about control flow. This is also one of the lectures that David and I renovated this semester. We always felt that the lecture, was a little bit dense. So what I did was I expanded about half of the lecture into a whole lecture, and hopefully, we will have better examples this time to take you through the real issues with control flow and make it, pretty clear how you end up doing, for example, scan for next week. Okay. So we're going to, the objective, lecture slide 2. Objective is to really understand the implementations of control flow on G80, and especially there are two things that we need to somehow understand both, but in a somewhat separate way. One is the branch divergence overhead. That in itself is going to cost you extra cycles. And the other one is streaming multiprocessor execution resource utilization. Oftentimes when you have divergence, you also will have resource utilization problems. On the other hand, you may also have resource utilization problems even if you don't have divergence in some cases. So, I want to make sure that you really have a good understanding of these two related but somewhat separate concepts. And then, obviously, knowing these things are just not good enough until you can write better code. So that's the real purpose. We want to make sure that you understand what a better piece of code looks like compared to a piece of, not so good code. And to understand compiler and hardware predication design to reduce the impact of control flow. Sometimes you can actually get away with a little bit of control flow, and the compiler will actually kind of cover it up for you. And I'm going to, tell you how that is typically done, and how you might be able to predict if the compiler is going to do this. So just kind of very quick terminology overview. We have threads, and these threads are the concurrent code associated state executed on the CUDA device. Okay, so remember all these threads are executing the same piece of code, right? That's SPMD. That's the most important thing here. And so it is the unit of parallelism on CUDA, and there's really a difference between CPU and GPU in the sense that the GPU threads are very, very low cost. And they also have this relationship in terms of warp in the G80 implementation. That is a group of threads that execute physically in parallel. And that's a 32-thread unit. And we're going to actually focus a lot on that 32 unit today. Okay? And block is a group of threads that are executed together and can share memory and a single multiprocessor. Remember, there are up to 512 threads in a block, right? And so there are 32 threads in a warp, so there are up to 16 warps in a block. And when we come to resource utilization, these are important numbers to remember, and we're going to come back to this point. A grid is a group of thread blocks that execute a single CUDA program. And you also need to remember that until all the threads in a grid have completed, the next phase of the program will not start. Okay? So if you have some threads lingering along, okay, in the grid, it's a bad thing because a few of them may actually take a long time to finish, but during that time nothing else happens. Everything has to finish before that grid will terminate and the next phase of the program will start. Okay, so that leads to the resource utilization issues. So how are the thread blocks partitioned? This is just kind of a summarize. Thread blocks are partitioned into warps and 32 threads in a warp. And the thread IDs within a warp are always consecutive. This is something you can depend on even into the future. Okay, in G80, G90, G100, whatever, all the thread IDs within a warp will be consecutive and will be increasing. The warp size could change. It could be 16 threads per warp, could be 64 threads per warp. It depends on the particular technology generation that makes sense. So that's something that you cannot depend on. Warp 0 always starts with thread ID 0. That's also a property that you can always depend on. Okay, that will be kept through the generations. The partitioning sort of will be the same. That is, you will always have consecutive chunks. Okay, but the size of the consecutive chunks could change. There's one thing that we really want you to remember. That is, do not rely on any ordering between warps. That is, you remember I show you that scheduling diagram, okay, where warp 0 could execute after warp 5, okay. They are all scheduling units, and they will just schedule whatever things make sense. And if you somehow depend on the order that warp 0 will execute before warp 5, it may work by accident in some of the generations, but then it could be endless trouble later on. Okay? Never depend on any kind of ordering between warps. And I'll make it even stronger. If you have some kind of dependence within a warp of 32 threads, there is a technique that people sometimes use called cascading in the field. That is, you actually somehow figure out that 8 of those threads in your warp will execute before the other, and you somehow produce result, and then, magically the result got used by the later threads in that warp correctly. Do not do that, okay? Because in the future, if the warp size gets reduced, you can immediately expose bugs. Okay, that's a very dangerous thing to do. And I have seen real code using that kind of technique. So let's go into the control flow. The main performance concern with branching is divergence. If you have an if then else, or you have a loop, you have a while loop, for loop, all these things eventually translate into a branch instruction. The branch instruction could go back in the case of for loops or while loops. The branch instruction can go forward if you have an if then else statement or exit of the while loop. So these things all get translated into a branch instruction in the instruction stream that will make some kind of decision. Okay, and that's how the conditions are tested and implemented. Different execution paths, because of a branch, will be serialized. That is, if you have an if then else, conceptually what you can think of is the hardware will actually figure out if all the 32 threads in that warp will go in one, just follow the then path, or in some cases it will figure out whether it's always going to, all the 32 threads will follow the else path, or in a more general case, some of them will follow the then path and some of them will follow the else path. Each one has a different performance impact. If all the threads follow then path, it's minimal overhead. Okay? Meaning that if no threads will follow the else path, then the hardware mainly just execute the if path, and things are okay. Same thing with if everyone goes through the else path, then the hardware will just execute along the else path, and very little overhead. What really happens when you have both is that the hardware will actually take time to follow the then path, and then it will reset, okay, and go back to the beginning of the if then else and follow the else path. These two steps are done sequentially, and in each phase, in each of these two steps, only part of the warps will be activated. So you will end up using resources almost twice the amount of time if you have two equal length paths. And each time you'll be using less than full resource. Okay? And that's a very wasteful way of executing a parallel program. So that's the divergence problem. Okay? So a common case is that you typically will see the divergence when people use indices. thread indices to make decisions. So a very simple case is you say, oh, I'm going to do a test in my code and say, if my thread ID is greater than 2, I'll do something. Else, I do something else, right? So only the first 0 and 1 threads will do, what you want, and then the rest, you want to skip. But this will create 2 execution paths. One path, one step will involve those 2 threads, 0 and 1, okay? And the other step will involve threads 2 through 31, okay? So the branch granularity in this case is less than warp size. However, if you say, if the thread ID divided by warp size is greater than 2, this means that you take, remember this, the thread ID is within the block, right? So it can be anywhere from 0 through 511. So if you say that the thread ID divided by warp size is greater than 2, that means you're going to activate the first 2 warps, okay? And you're not going to activate the rest of the warps. So in this case, every thread in the first 2 warps will be executing the then part, right? And all the threads in the remaining warps will be executing the else part. And there's no divergence within the warp. For each warp, they will not require 2 separate steps to go through all the threads. Okay, so that's why in the second case, there's no branch divergence. Okay, so once this should be pretty clear, right? So now let's go into some real examples. Make sure that it's really solid before we start to look at code examples. So let's look at something, the parallel reduction, and since given an array of values, reduce them to a single value in parallel. And this reduction doesn't have to be a particular type. It could be a sum, okay? The very typical thing to do with reduction is to calculate the sum of all the array elements. But that's not the only case that you will do reduction. You could also do something like max. Okay, you can do a maximal, find the maximal of among all the array elements. So you could, a typical way to do maximal is you find the bigger one between each pair, and then you find the bigger one between the pair of pairs, and eventually you find the biggest one, right? So in some ways that instead of doing an add, you do a compare and then swap. Eventually you will get to the maximal. You could find minimal, okay? You can find products. So all kinds of things that you can do with reduction. And typically when you do reduction, you want to use on a parallel machine, you want to do reduction in a in recursive or something like a logarithmic algorithm. If you use a sequential machine, reduction is a little bit, it's usually a linear algorithm, in the sense that you can actually, let's say you do the sum, it's fairly easy to do. You just kind of, keep reading each element and you just sum it up, right? So that's you only need to touch an array element one time, and then you're done with it. So in a sequential machine, when you just scan through the array, okay, sequentially, and each time you add that to a temporary sum, and that gives you the fastest execution. That's the sequential machine implementation. But in parallel machine, oftentimes we're willing to spend more, steps. But hopefully these steps can all be done in parallel. If you go back to the sequential implementation, when we take a partial sum and take one element at a time to add into it, every step is sequential. You need to finish the previous step before you can actually go into the next step. It's a fairly sequential algorithm. And if you have 10 million elements, right, in a vector, then it takes 10 million steps, and these 10 million steps are all going to be one after another. So that's how you get into trouble with these large data structures. So now if we use something like G80, what we want to do is we want to use the sort of the recursive reduction type algorithms. That is, we're willing to, to do these things to generate multiple partial sums, right? So we will take each pair and generate pairwise reduction, and then we'll take, we'll look at those pairs and then we'll generate another pair. And this will take, essentially a log 2 of the vector size steps before that tree will eventually converge into a single element. Space-wise, we'll be using multiple partial sums, right? Because we're going to, we'll be simultaneously adding things together. So we'll have more space usage. So that's why when we use parallel machines such as G80, we typically use what we call the in-place reduction algorithms. We will keep the original vector in the device global memory, okay? But we're going to actually load whatever we're going to reduce into the shared memory. And we load them into the shared memory, and we will reduce them in place, meaning that we will actually, essentially they will be partial sums. The way we look at them is, when we load all the vectors into the shared memory, there are partial sums of ones, right? Each one is also its own partial sum. And then after the first step, we will actually generate pairwise partial sum, and we'll overwrite some of the, some of the elements. So we will, for example, in the first implementation, we will overwrite all the even elements. So all the even elements will become pairwise partial sum, and then we will keep, just keep rewriting the partial sums until one of them becomes the total sum, right? So this is an in-place reduction in the shared memory, and each iteration will bring the calculation closer to the final sum, and the final solution will be in element 0. Okay, so fairly straightforward. And we also talked a little bit about that in the memory banking conflict, right? So it shouldn't be all that unfamiliar. So let's look at a simple implementation, and we'll kind of analyze it a little bit about its performance characteristics. So we will assign the thread ID to T, and so we will start with what we call stride as 1. So essentially, we will we will have a stride that will be 1. And then we will multiply by 2 every time. So it will be 1, 2, 4, 8, 16, 32. Right? All the way until stride reaches the block dimension. That is, the size of the block. So that will be the chunk of the data that we will will be adding up. So in terms of the bigger picture, if you're summing up a large number of vectors, more than 512, what you would do is you will have each block, right, to generate a partial sum of 512 elements, and then eventually we'll just kind of put them all back together, right? So that will be sort of a 2-level picture of that. But now we're going to be focusing just on the computation within that block. So in each step, we will synchronize, meaning that we will make sure that all the threads have finished the previous iteration. Okay? So remember, this is a partial sum thing, right? So, each thread will be independently doing some partial sum. But before you go to the next iteration, you want to make sure that the previous step has been completed for all the threads in that block. Then you can safely take the partial sum from that step and generate the next one. So that's why you will have the same thread before you go into the next iteration, right? Okay, so what we will do is we will, in this simple implementation, we will say if the thread ID is a multiple of 2 times stride, then we will do this. We'll do the partial sum addition. But if you're not a multiple of the 2 times stride ID, then you will not do anything. Okay? So this essentially can be viewed from this simple picture here. So what I will do in the first iteration is I'm going to take, remember stride is 1. So I'm going to take, the thread ID and the access one element and the stride ID plus stride, thread ID plus stride, which is 1. So I will have 0 and 1, and 2 and 3, 4 and 5 in the first iteration. So I will generate all these partial sums. So when I look at it carefully, I will see this picture. Okay? So I kind of color-coded the picture to reflect how the threads will work. So let's start with the orange thread. The orange thread is, the thread that will essentially execute for most of the time on this machine. You will start with the first iteration. We'll add elements 0 and 1. Okay, and stride at this point, at this point is 1. So essentially, when you do the division, you will have this thing will be will have a remainder 0. So this thing fits that first test, and you will execute this first step. However, thread 1, thread 1 will fail that test, right? When you do the remainder test, thread 1 will have a 1 rather than 0 remainder. So right from the beginning, thread 1 is not going to do anything. And we already created a divergence for that branch. The first, thread 0 will have an execution, thread 1 will not have an execution, so you already have that divergence going on. And so these two threads, thread 0 and thread 8 in the picture will execute multiple steps. And then if you look at the next thread, thread 2, it's kind of an interesting case here because in the first test, it will be a multiple of stride. So that's why you're going to execute that 2 plus 3. But as soon as the stride becomes 4, remember stride will be multiplied by 2 every time. Then when you divide 2 by 4, the remainder is no longer 0, right? So you will be disqualified for the next step, which is what you want because whatever you calculated already got incorporated into the partial sum, so you don't really need that thread to execute anymore, right? Which is reasonable. So if you just look at the picture, I use the color-coded picture to show that some of the threads will execute for more times than others. And once you get into the yellow one, the yellow one will execute one more step than the green ones, but eventually it will also be turned off. So let's make a few observations about this execution. Any questions about this execution? Okay, good. In each iteration, 2 control flow paths will sequentially traverse for each warp. Okay, so in that for loop, you will end up seeing 2 different control paths. And threads that perform addition and threads that do not, right? So, it all depends on, if there are multiples of the stride at that point. And threads that do not perform addition may cause extra cycles depending on the implementation of the divergence. That is, remember, this is a kind of an easy case where, you either do the then part or you don't do anything, right? So you can easily imagine that if you don't do anything, there could be some kind of implementation, right? That says, oh yeah, I don't need to do anything, so I don't need to do that second step. But it depends on how smart the hardware implementation is. It may also cost you just a couple cycles just to figure out that there's nothing, right? So these are implementation-dependent kind of things that you cannot really rely on. No more than half of the threads will be executing at any time on this machine. Okay. If you look across all the blocks, okay, if you look across all the warps, no more than half of the threads will be activated at any given time in this piece of code. Okay? right from the beginning, remember that thread 1 was already disqualified, right? So right from the beginning, you'll have no more than 16 threads actually executing in that warp. So that happens in across all the threads in the grid, right? All the blocks, all the warps, everything. Okay. So you immediately took away half of your resources from the execution. Okay. And what's really happening is each warp will be executing kind of in a kind of a handicapped way. But all of them will kind of make slow progress. Okay, all of them will make slow progress, but all of them are making progress in a handicapped manner. So, on average, less than 1/4 of the threads will be activated for all the warps over time. If you look at sort of the reduction, okay, the initial first 4 or 5 iterations, you will have half in one iteration, 1/4 in one iteration, 1/8, 1/16, right? So across those first few steps, there's going to be, essentially less than quarter on average, right? If you look across on average, less than 1/4 of the resources will be used, right? After that, it gets even worse. Okay, after that, you will have, entire warps in each block will be disabled and what. So, but remember, until all the warps of a block finish, that block will still occupy an assignment unit in the SN, right? So until all the warps complete, that block still occupies that space. No other blocks can come in. Okay, not a good situation, right? So, but after the 5th iteration, warps will begin to turn off. Because you will have, essentially at that point, every warp will either have 1 that remains to be sum or 0. Okay? So that 1, for the warps that still has that one thing that has not been accumulated, eventually something will happen, right? So, it will take place at some point, and it will take up to another 4 iterations, okay, for all the warps to go away. So you have 4 iterations of, within each warp to go down to 1 element, and it will take, another up to 4 iterations if you have a 512 thread in order to, eventually go down to 1. So at that point, you retire the block, okay? And you will be using, resources in a fairly inefficient way. So on average, you will have far less than 1/4 of the resources being used throughout this piece of code. And if you get anything more than 1/4 of your peak performance, there's something wrong with this. Okay, then I need to understand how you got it. Okay, so this is the intuition I want you to have. When you look at some of this code, until we have much better programming tools, this is the intuition you need to have. Okay, but in 10 years, if these guys build good enough tools, then you don't need to have this kind of intuition, right? What are the shortcomings of the piece of code? Well, there's one is the divergence because of that test, and one is actually you need to go back and review this a little bit if you don't remember, there's a bank conflict in access. So you will actually have wraparound access because each thread is actually accessing 2 elements, consecutive elements. So you'll be wrapping around once, okay, in your code. Okay. So these 2 things can be both addressed with a better implementation of the algorithm. It actually looks pretty similar. It's not dramatically different. I still use TS thread ID, but I will start the stride as a block dimension. So I will start with the biggest stride, right? And then as long as the stride is greater than 1, I will continue to divide it by 2 with the shifting, right? Divided by 2 every step. So instead of throwing out, I will be, coming in, right, with my strides. And then, I will still do the synchronization because I'm doing the partial sum. And then, if the thread is less than stride, okay, so So every time, every iteration, as long as the thread ID is less than the stride, I will do the addition. When I do the addition, I would do the current position plus stride. So in the first iteration, what I'm going to do is I'm going to do the stride number plus half of the dimension, right? And then I will just, in each step, I will bring it closer in. So I would actually do, this is a 32 element picture, and I'm going to go back to the bigger picture as soon as we finish this one. So instead of adding two neighboring elements, I would be adding element 0 and 16 in the first iteration, and 1, 17, 2, 18, and so on, right? So I will be adding, essentially, I'll be doing a shuffling, almost like a shuffling of cards. So I will generate, this is actually a kind of a shorthand because I have some dot here. So that first iteration, I will end up with 16 partial sums. But they're all going to be densely positioned. And I'm going to generate 8 partial sums in the second iteration. That's why I labeled the iteration to be a third, because this is where I have come down to 4, right? And then the fourth iteration comes down to 2, and eventually I have 1. So as soon as I get to 32 partial sum elements, it will take me, 4 entire iterations for me to go down to the final sum. But there is also a slightly bigger picture here. That is, if I start with 512, I would actually, start from very far away, right? So, it will take me a few iterations before I condense everything into 32. And that will take 4 iterations. So this is a reverse process of what we just had before. The process that we had in a simple implementation, it will take 4 iterations for you to get rid of all the data elements within the warp, and then you start to retire warps, right? And here, we actually will use half of the warps. Okay, we'll use half of the warps to keep retiring the sum until they get into 1 warp, right? And then once we get to the 1 warp, we will actually begin to do the 4 iterations. If you look at the computation, what happens is that we're going to, right from the beginning, we're actually going to have only half of the warps active, right? The other half will actually fail the test, okay? So the other half will now, be idle. But for the half of the warps that are active, they will be all working full force, okay? They will be all the 16 threads will be adding, okay? And then you will retire another half of the warps. The other half of the warps will not disqualify all the time. There's no branch divergence within those warps. They're all dead, okay? So, but all the quarter of the warps will be executing in full force, okay? All the way until you hit the last warp, right? And that's where you will have, eventually you will have branch divergence in the sense that you will still have, situations, the last few iterations, you will have branch divergence because within the warp, you will still have ones that qualify and ones that disqualify. But that only happens to the 1 warp, okay, that remains in the end. So all through the execution, you will be executing these warps at faster rate. Fewer warps, faster rate, okay, until you hit the last warp. And that last warp will have divergence. Okay, make sense? Good. I think this is the part that we didn't explain properly last time, and we're skipping over a little bit. So hopefully, let's make that observation. So entire warp will be shut down as iterations go on and better resource utilization. And recall, when one big benefit here is there's just no bank conflict anymore on the shared memory access. Okay. So if you look at it and say, you know what, I can actually make things a little better here. Okay, I can actually make a further refinement. Remember that, you know what, I talk about this, you know what, this thing about, you know what, you are going to, you're going to be, all the warps are going to be executing full force, or the active warps will be executing full force until the very last one. Okay? So, one way to deal with that final divergence is that instead of letting it take, you know, one iteration at a time, and in every iteration you detect branch divergence, and you will do the branch divergence in every iteration, you can actually just say, I will stop. You know, whenever I reach the point where I know there's only one warp left, okay, and I will just, you know, go back and roll the loop 5 times, because I know that there will be, you know, several final iterations where my if then else will be wrong. And so whenever I do this, and then so I will unroll the loop, and so what this is going to do is it will actually take the final several iterations and then just explicitly do one instruction, you know, for each iteration. And then you will just do these computations without doing any kind of branching. So you will be doing some extra computation. There will be some of the threads that will still be adding, okay? And their results will not be used, right? The only ones that will actually lead to useful results are the ones that I marked as red in the previous picture. However, those wasted results are okay because they don't take extra time to compute, okay? So they will be, you know, also busy, you know, consuming some resources, but they don't take extra time. For the ones that you do need, you will be able to crank through them faster because you no longer execute the if and else and, you know, all the branch divergence kind of testing. Yes?
If the warp size are different,
yes,
is that code still correct or not sufficient? But it's still correct?
Yes. The code will be correct, but it may not be efficient.
If the warp size changes,
yes,
this, especially if it decreases, this code might not be correct because you've taken out the synchronizations in the if state. So there's an implicit optimization that you made there that a warp is synchronous with itself.
I forgot about synchronization here. Yes. So it will not be correct. So take this as a forget about this optimization, I guess. So I should forget about this optimization.
This is sort of a very architecture-specific optimization. So a warp is synchronous with itself. So in this case, you can eliminate the synchronization between each of the steps once you get down to the last warp. But if the warp size changes, things could be different. This might not work anymore.
Yeah, in fact, this is exactly the cascading thing that, you know, I was actually talking about, right?
Is the warp size exposed to the program?
No, it shouldn't be.
Not right now. No, it's not.
Yeah. I saw another question. Same question. Right. So, put it this way: you could have a situation where the warp size will go down to 1 in the future. Okay, it is highly likely in a few generations the warp size may even go down to 1. So, you know, forget about this.
If you put in the sync thread between each line,
yeah,
does it cost you a lot since it's all running in one warp?
The code should not run any worse than the previous code.
But a sync thread waits for the entire block.
No, it's still okay. It's still pretty much okay. Let me go back a little bit. So, because we took away, so if you look at the sync thread, if you just put a sync thread between each one, then, you know, you shouldn't be executing any more sync threads than the previous one. However, there's a danger to this kind of stuff. Because, if you look at the sync thread, this is guaranteed to be executed for every, for all the threads. If you do sync thread in an if then else statement, some of the threads will not execute that sync thread. Okay? Is that what you're going to do? Say yes. So, chances are it's going to cause you trouble because theoretically sync thread is something that every thread will need to report and say I'm here. Okay? So if you do the sync thread thing, in this code, I think it's actually going to be problematic regardless how you do that. Even if you add a then part or something, it's probably still going to be problematic. So that's why, I said, forget it. Because as soon as you mentioned that, I said, okay, I don't see any reason, any way for me to correctly do this piece of code and will scale to the future. So, okay, so treat this slide. In fact, I'll change the title of the slide. I will say, a tempting refinement that should not be done. Yes?
Shouldn't the sync threads be at the end of the for loop?
No, yes or no. Essentially, what this one does, because it depends on when you loaded the stuff into the shared memory. So if you load the stuff into the shared memory, having a sync thread at the beginning of the for loop will allow you to sync and make sure that all the things are properly loaded. You see what I'm saying? Otherwise, you will have to have a sync thread, after that loading process before you go into the loop anyway. So you're not going to be saving anything.
Well, I was wondering about that last add though.
Because on the other hand, when you exit the for loop, the last computation needs to be synchronized before you go into the unrolled part.
So maybe
so there has to be a sync thread here.
Right.
Yes.
So either way,
That's the other bug.
Yes.
Yes. So we have 3 bugs in this piece of code. Okay? The concept of predicated execution is fairly simple. Before 9/11, I used to explain it in a somewhat different way than what I do today. It's an instruction that accepts an additional operand. Okay, and this operand is a Boolean operand. It's either true or false. So if the Boolean operand is true, the instruction executes normally. If the Boolean operand is false, the instruction is treated as no on. So predication in a piece of code typically looks like this. If you have an if then else statement, let's say if x is equal to 10, then you do the addition of C. And this is slide 18, and so what you would do with predicated code is that you would do the testing of x equal to 10, and then you would set a Boolean variable. So this takes an extra instruction, okay, to set that Boolean variable. And then the Boolean variable will be used by the load of C value, do the add, and then store the C value. So that after the execution, if x is equal to 0, then all these instructions will take effect. If x is not equal to 0, then none of these things will take effect. Okay? So you will always end up executing this piece of code regardless of the condition, but the Boolean value will make sure that the instructions take effect the right way. So if you look at the original semantics, what happens is if x is not equal to 0, you should be skipping over C, get C plus 1. But here, you will do that anyway, but you don't let the effect take place. There's a subtle difference here. The difference is, if you have a huge number of code instructions in the thing, then skipping over is a better idea. Okay? If you have a huge number of instructions, then you will end up processing a huge number of instructions and not let them take effect every time you go through this piece of code. So that becomes a bad idea. But if you only have a very small number of instructions, such as 1, right? Then suddenly the overhead of skipping over an instruction and cause divergence and so on may be much more than just always fetching that instruction and execute it without any kind of divergence, but it only takes that one instruction every time, for all the threads. And some of the threads will take effect, some of the threads will not. So this is what predication means. If you look at a typical if and else kind of code, in the source code you will have the then part, you have the else part. And when you predicate, what happens is you will assign the Boolean variable into each instruction, and then you just go ahead and mix them together. So B and C can actually get mixed together in the assembly code. So the first instruction of B and the first instruction of C could just side by side, okay, and then the other ones. So this will typically give you more independent instructions after a load, for example, okay. So oftentimes you can absorb that the extra instructions with with the low latencies and so on. So just to give you one simple example, we'll have that if the else statement, and so let's say register 5 is equal to 10, and then you will assign the true part to P1 and the false version to P2. So essentially it was P1 will be true and P2 will be false if the condition is true, and then P1 will be false and P2 will be true, the condition is false, right? So it's just a pair of predicates that will always give you the condition and its complement. So then what we'll do is we will take the then part and predicate them all with P1s, right? And then we'll take the else part and predicate them all with P2s. Once you predicate them together, you can actually just do this. You can actually make progress simultaneously on the then part and the else part. You have the first instructions of the if part and the then part and the else part, and then the second instructions of the then part and else part, and so on. That the execution progress can be made. In fact, these two could all be both loads. Okay, in the first instruction of the then part and else part could be both loads, so you can initiate the loads at the same time. So what happens in G80? Okay, so what we just talked about is predicated execution in general, and this particular feature is actually used very widely in most of the architectures today. If you look at x86, it's called condition move. Okay, so there is a predicated instruction that does it, and if you look at Itanian, there's a very broad range of predicated executions, predicated instructions. In fact, some of these Intel people still blame me for getting them to use the predicate execution in their architecture, in the Itanian architecture. So essentially on G80, you will see a comparison instruction that sets a condition code. Okay, and so there's only one. Okay, this how many condition codes are there in G80? Do you remember?
I don't remember off the top of my head.
Okay, let's just say kind of one. Instructions can be predicated to write results only when the condition code meets the criteria, such as condition code is 0 or condition code is greater than 1 and so on. And then the compiler tries to predict if a branch condition is likely to produce any divergent warps. So if guaranteed not to diverge, then only the predicates if it is less than 4 instructions. If it's not guaranteed, only predicates if it's less than 7 instructions. What this says is that in the code that we're talking about, okay, remember, when we did the second implementation of the reduction, the compiler will know that that piece of code is guaranteed to not diverge. So you will take a look at the instructions in the then part, right? In that then part, and say, oh, it's less than 4 instructions, so it's tolerable cost that I have to process them all the time. So the compiler would just go ahead and do the predication. And if it's not guaranteed, then the compiler will take even more risk, meaning that even if the then part takes 7 instructions to execute, as long as the compiler says, oh, there's probably going to be a divergence in the SN, then it will actually take up to 7 instructions and predicate it. This is just a rule of thumb for you for this semester. That particular compiler decision could change in the future. Okay? And so it's not something that you should rely on for cross generations. Especially the number could actually both increase and decrease. For a future generation, if they started to be able to issue more than 1 instruction per clock cycle in the SP, they may increase the number. Okay, but in the generations where they may have some other considerations, such as they may have some kind of some kind of reduction in the branch divergence cost, then they may reduce the number. Right? So it's something that you probably should not take very seriously when you write these scalable code in the future. And all the predicated instructions take execution cycles. And those with false conditions don't write their output, and or invoke memory loads and stores on this particular machine. So you were just one step ahead of me, but that's great. So 6 branch instructions, so can be cheaper than serializing divergent paths. Okay.